Hello community, great that you are back. We have a new QwQ 32B and you know what? Compared to R1, it just uses 24GB of VRAM. Have a look at this. Now I know 3 months ago I already did some videos on QwQ, but this was the preview version. And 3 months ago we coded and I was really impressed by the code abilities of this. But now, today, on March 5th, we have now the brand new official non-preview version. And I have to tell you, by Alibaba's Cloud Qwen team, this is really impressive. So let's have a look. We have Apache 2.0. You can download it for free. They tell you here, yeah, QwQ, just 24GB for hardware requirement of VRAM compared to DeepSeek R1. I mean, the real non-quantized version, 1.5 terabyte of VRAM, and they give you here how to install it locally, install Olama. So interesting. I want to do a different kind of video. I want to show you the performance of QwQ 32B, but for a long chain of thought reasoning. This is a beautiful reasoning model that has some exceptional stability. And I want to compare this to a Gemini 2.0 thinking model. And I want to show you, if you use tools, what are the acceleration factors in speed that you can achieve. So, QwQ, long chain of thought, beautiful instability, and then we will make a speed run with Gemini 2 if we use here the appropriate tools for this. If we go back here to this long chain of thought, I can tell you it will take some time. And you will hear me explaining to you here the verification, the backtracking of QwQ, the error validation of QwQ, the correction factors that is in place. So I will comment live on the performance of QwQ. And if you think, what are the topics that I'm presenting you, you will find a solution here in this video where I show you what are the most important things here for a long chain of thought. The query is identical in both cases. So this is an identical query. This is my elevator example I use now for more than 11 months. You find this on all my other videos here, GPT 4.5, Sonnet 3.7. Now on the other hand, if we use QwQ, the thinking mode, this is beautiful, this is available. But you will see the tools are not available yet officially. So this is the whole difference, but let's start the testing. QwQ 32B, brand new model. So, how can I help you today? Well, we do a test. We do here the elevator test. Remember my beautiful elevator? You want to go to floor 30 and there are some elevator rules, button A, B, C, D, E. And this is it. I have this thinking mode activated. So let's see what it is able to do. It is thinking, great. We can see the thinking. I do like this. Great QwQ. Real nice. Button A. We are here in real time. Okay. Send a message. It's a preview model still being updated. So this is the first look at QwQ 32B. Okay. Maybe it is floor 2. So it makes sense. So landing. So you really see here the thinking process if you want, the algorithm. No, this is not possible. Alternatively, we should go to this floor. So let me note it down. Button B moves up 4 floors, but subtracts 3 from the new floor. Okay, goes through an example. Yep. Can be summarized in the following way. Beautiful. Button C moves down 7th floor. But if the floor you land is a prime number, you immediately bounce back 10 floors. Yeah, great. Okay, it understands here exactly what I wanted to do here in this elevator example here, this logic test, button D. So it's really looking here in detail here at my instruction, really trying to understand absolutely every detail about my instruction, arguing about it, trying to find the pros and the cons. And only if it thinks that it's understand what it's talking about, we go on. Effect. Trap floors. Trap floor 13, trap floor 22. Yes, beautiful. Now the challenge is to find the shortest sequence of button presses. Exactly. So let's think about the strategies. Thinking about strategies. Okay. Let me consider possible first moves. So from 0, it is A, B, C, D, or E. Absolutely. Option 1, starting from D. Okay, another option. So it's really trying to argue its way through this process. So if you think about this, we could easily abstract this away to a mathematical notation, to a Python code notation, and this would then be easily solved with some Python algorithm. But no, we are trying to solve this here in natural language. Okay, so it's trying to be as logic as possible. Not bad. Okay, let's give it time. This is a reasoning model, no problem at all. We're in the thinking mode, QwQ 32B. Yep, pausing 3. Alternatively, so pressing D or C can both lead to 21. Yeah, so there's quite a lot of possible alteration. If you check out each and every possible combination of buttons you can press in this very particular logical elevator. Okay. Found a 10 press solution. Okay. Options. Not pressing D. Alternatively, another option. Next multiple of 3. Okay. Pressing then. Okay. So we're really trying to be as logical as possible. Think about each and every combination of the logical steps that will take us here to the different floors. 13 takes, that's a little bit too much. You and I, we both know that the solution is 6 presses of buttons here. And we go from 0 to 30. But what are those buttons that we have to press? Wow, it's really, really thinking about this. Look. Can't press here. Let's assume this is impossible, so I have to go this, pressing this here. Alternatively, there's another route. The same as above. Maybe there's another approach, starting now from 0, pressing E, no, pressing B, no, perhaps pressing button C is more advantageous. No. Alternative floor prime, C from 12. Pressing C from 14, no. Alternatively, starting path. Wow, this is not a path. So bounce to 15. So it's really thinking. Now maybe this is a good thing, you know? We have to wait for the result. But you see, this could be transcribed in a very short Python code and solved within 2 seconds. So sometimes it's not that good if you really try to find here a verbal explanation of everything. My goodness, how long will this go on? The total steps, okay. That's better. So we have down to 9 steps. 9 steps is okay. The optimum is 6 steps. So does this mean we have to go down now this path? But you know, this is the first view of the QwQ 32B. Let's see what it is doing. It gets all the time it needs. But I have to say, quite impressive till now. Okay. Not helpful. Okay. As before. Now it's finding here a solution it already encountered. Let me see another path. Still thinking hard. That's longer. Alternative, another path. That's bad. Another approach. Let me re-examine the button A effect on 7 again. This is nice. This re-examination, this self-reflection. Trying to find here it's 8 steps. Hey, 8 steps. That's good. So now we have an 8-step solution. You know, it's a 6-step solution in the optimal case. That's better. Why didn't I think of this earlier? This is the better path. Okay. Let's continue. Can we do even better? Let me see if we can shorten further. Alternatively, alternative path, another alternative path. My goodness, it's really going through each and every other path. My goodness. You know what's really impressive is the persistence with it's trying to find a solution. A human would have given up after, I don't know, 200, 300 paths, yeah? But no, here we go. 8-step path. Okay, we are still at an 8-step path. We are still thinking. Beautifully. Still 8 steps, okay. Alternatively from 11 path, let's see. No, that's a big jump. Wait, let me verify. Internal verification. So nice. This is a pattern that we will discuss, or we already have discussed, depending when I will post this video. Shortest path, 6 steps. That's the shortest path so far. Is this valid? 6 step. It found the shortest path with 6 steps and already. And now it's asking itself, hey, can I do better? That's 7 step. It's worse than the 6-step path. He'd already found a 6-step path with this kind of logic augmentation. You see, we had a self-reflection, we had a self-correction, we had a self-refinement. Nice. 6 steps. Is there a path with 5 steps? Let me think. No improvement. Another path. We are here in real time. I don't accelerate, just wanted you have a feeling here for this model. It's really going strong. I don't know how many minutes we're in, but it found the solution with 6 steps. Impressive. Just by verbal logic, English sentence deduction. Okay, still trying to find a shorter path. Can we use button E more effectively? It really goes through all the possible paths. Wait, what if we use button A? Yeah, let's do a shorter sequence. Same as before, so the path is valid. So is there a way to reach 23 in fewer steps? It is segmenting now the problem in subtasks. This is extremely important. If you have a complexity of a task that is really high and you subdivide the task in a multiple tasks that have a lower complexity, beautiful. So we see here all 4 characteristic logic patterns that are essential for a self-learning AI system. 7 steps. No, we already had 6 steps. That's solution. 6 steps is the minimum. Impressive. It found the minimum solution with 6 steps. So now I ask, is the path D, AB, AB, D also a solution? So the user is asking if the path is a valid solution. Let's check this, starting at floor 0. Goes step by step. Beautiful. Yes, that works. D, A, B, A, B, D. So the path is valid. To check if there are any other, let me check if there is any mistake here. It validates itself. This is really nice. But wait, we're missing something. Let me check again. No, 6 steps. Okay. Is indeed a solution. And yes, now comes the answer. And the answer is yes, the path is also a valid solution. Here, step by step. Breakdown. Real nice, real beautiful. Why is it valid? Beautiful. Multiple option part. Great catch. You found another valid route. Emoji. Absolute beautiful performance. It could have been solved by transcribing it to a Python code environment using here a Python tool, but just by logic, impressive. Absolutely. So, and now we come to the part where I tell you, okay, Gemini 2.0 flash syncing experimental. My goodness, from 21st of January of this year. And please have a look here at the token count. You will be impressed by the token count. I go with the classical temperature predefined here by Google for me. I will no system prompt. So I really just naive go into this. And the only thing you will see me do is I will execute here. I will use one tool for this job. So here we are with Gemini. We just paste in here this beautiful test. You know, here this is my skyscraper elevator test. Yep. Go to floor 30. We have bottom A to E. I have 2 trap floors. So let's go. Yeah, we want to see it thinking. Yes, of course. We want to understand what's going on. Look at this. It already identified here. Beautiful. Wow, this was too fast, but you see it converted here. It had some ideas, it converted. Code execution failed. No, it should be done in 16 seconds. Oh, we encountered a mistake. This is a demonstration problem. Hey, we found a solution. 24 seconds in, we found a solution. Isn't this beautiful? We found here, we have a POV ABAABD, and this is 6 button presses. This is the perfect one. So let's have a look what happened, because it was a little bit too fast. No, it should be done in 16 seconds, but we took 24 seconds because this is here a demonstration, and of course it went wrong, but we stick with whatever happens. So I need to find the shortest sequence of button presses. I will use here the first search algorithm for this. So I define here the rules as function. So each button press will become a function. I have here a function for is prime or not. Process to solve this riddle. Understand the goal, represent the state, define the button as function, handle the trap floors, choose the perfect search algorithm now for Python. Implement the search algorithm with a queue, with visited set with a specific loop, generate the next state, check for the prime number, output an explanation. I can implement a Python solution using this to find the shortest path from 0 to floor 30. So define a function, implement the algorithm, handle the trap floors, track the path, and output the shortest path and step-by-step explanation. Let's do this. I will use Python for this. And all of this in 9.9 seconds. So now we have the strategy. Now we start. Now we are coding. I mean, Gemini is coding, but we are coding. We are checking here, move A, beautiful. We define what it is, the button B, and the button C is defined here, simple mathematical Python notation, the button D, and the button E. So our 5 buttons are now Python functions. Beautiful. Yes, this is still me. The user wants to solve this, and now to the algorithm. BFS, initialize a set to keep track of the visited floor. The queue is not empty, handle all the different elements, and implement this in Python. So we start coding, Gemini starts coding this in Python. You see, handle the trap floor 22, beautiful, the allowed buttons A to E. And now the button B, the button C, the button D, the button E. Beautiful. We just have a Python optimization here with a simple BFS algorithm, step-by-step explanation, even at the end. Beautiful. So it tells me, hey, this is a solution and this is a solution because for the button B, then we have button C. Yeah. Here we have button E. Beautiful. And if there's nothing, we say no path found. Execution failed. Why? The move A is not defined. My goodness, come on. We could have found a solution in 16 seconds, but no. Look, it's self-correct itself. Beautiful. So I say, hey, I found that it's not available in the scope of the second tool block. So to fix this, I need to include the function definition with the same tool block. Yeah, that would be beautiful, yeah? So I just copy the function, integrate everything in one, include the function in the same execution block, and let's run this again. Okay, so again, it's self-corrected without me doing anything at all. Move A, move B, button C, button D, you know this, but now everything is in one execution block. Beautiful. Solve this. This is what we want to achieve. Handle the trap floor 22, all the available buttons. Again, we know this. And here we go, A, B, C, D, E, and then beautiful. And if no path found, we say, hey, there was nothing, but if we found the shortest path, we say, this is the explanation why this is here the shortest path, why this is a valid solution. So Python code is okay. Execute. Code execution. Here we go. A, B, A, A, B, D. That's it. That is the solution. Here we have a very short explanation why. Beautiful. We start at floor 0 and we go to floor 30 with 6 button presses in our elevator. So it took 22.7 seconds for this to finish the Python execution, and then this is the optimal path. So with BFS algorithm, the return path A, B, B, A, B is the correct path. And I said, hey, great, can you validate this? You know me. And since we're already at 24 seconds in, I said, okay, and comes back and says, yes, just checked everything. After meticulously stepping through each button press and verifying against all given queues, the path A, B, A, B, D is indeed a valid path. It is validated and the correct path. So this is it. Congratulations. And I have another path. I say, hey, what about the other path? And comes back and says, hey, you know what? This is also here a valid solution. Look, also 6 button presses, and here running through the algorithm, it took them 6 seconds just to verify that this is another optimal solution, equally effective as the solution that Gemini found itself. And then I have a little trick and I say, hey, can you decline that this is a valid path? And I define here another path, but it's not impressed here by my trick and says, hey, this is also a valid path. It also uses 6 button presses. So we have another optimal solution, and this just took 4 seconds to validate. Isn't this impressive? So completely take a problem, transfer it into code, into mathematics, and you can solve this in 16 seconds. Or you go here with, if you want, a verbal explanation. Yeah, in total 24 seconds, because we made a mistake, but it's self-corrected. It found a mistake, so good. It was a demonstration problem, but I think now I'm glad that it is, because you see it did it, and we only spent 6,700 tokens. Compare this to the 10-minute run. So there you have it, this beautiful video. You now understand what I find impressive with QwQ 32B. It has an extreme beautiful stability. Looking here at all the chain of thought augmentation, this long chain of thought, watching here 10 minutes of a system in real time arguing about here complex reasoning topic to find a solution, and it achieved to find a solution here in 10 minutes, a stable system. But also if you do the same job with the right tool, like a Python environment, you see that our LLMs more or less are already agents, because they know how to use specific tools that they have been trained on. So the speed improvement, if you use the right tool, can be absolutely impressive. However, you might not see here the human reasoning, but it will be transformed to kind of a mathematical code logic and then performed within seconds. So if you found this video maybe interesting, or maybe said, hey, I learned something today, why not subscribe? And I see you in my next video.